Good morning, everyone. We have Dr. Mina Namvari for our Nano Open webinar today. I would like to brief introduction before giving to screen to her. Dr. Mina Namvari, after finishing her bachelor's in chemistry at Tabriz University in 2002, started masters in organic chemistry and worked on the synthesis of organosilil molecules. However, she became fascinated with the emerging wonder material graphene oxide during her PhD. Her research was based on chemical modification of graphene oxide with organic molecules and preparation of related magnetic nanocomposites for wastewater treatment. In 2015, she moved to China and continued research in developing graphene polymer composites. She also worked in Czech Republic and South Korea before joining Sunum, where she carried out research on graphene-based single-atom catalysis for energy application and self-cleaning surfaces, respectively. Today, she is going to talk about the modification of graphene oxide towards wastewater treatment, fillers, and energy application. Dr. Mina Namvari, the stage is yours. You can share your screen.
Merhaba, benim adım Mina Namvari. Sunum ailesinin bir parçası olmaktan çok memnunum. Türkçemin çok iyi olmadığı için bugün İngilizce sunacağım. Thank you, Nokta Hanım, for the kind introduction. My name is Mina Namvari, and today I would like to talk to you about modification of graphene oxide towards wastewater treatment, fillers, and energy application. I would like to start with a brief introduction about myself. I did my PhD, well, I'm from Iran, and I come from a city in the northwest, Tabriz. I did my PhD at the University of Tabriz. Then I moved to Shenzhen in China to conduct research. Then I decided to go west and worked in Olamos for some time. And before joining Sunum, I was working in Busan, South Korea. First, I would like to start with a short introduction about graphene and its derivatives. High-quality single-layer graphene was first recorded by Novoselov and Geim, who pulled apart single layer with a Scotch tape from graphite. There are various methods to prepare graphene, such as mechanical exfoliation, liquid phase oxidation, thermal decomposition of carbon, silicon carbides, and CVD. It has excellent mechanical, thermal, optical, and electric properties. The zero band gap of graphene gives it excellent electromobility, but for the same reason, functionalization cannot happen on the surface. So here is where graphene oxide comes to the play. At the bottom screen, you can see the different steps to prepare graphene oxide and reduce graphene oxide. So I will refer to graphene oxide as GO from now on. The obvious difference between GO and graphene is the oxygen functionalities on the surface and the edges. If we go further for the reduction, reduced graphene oxide is obtained. It is similar to graphene, but it's not as good because pi-pi stacking results in the agglomeration and stacking of graphene sheets, which diminishes its intrinsic surface properties. But to prevent this aggregation restacking, modification plays an important role. There are three ways to modify the surface of graphene oxide: non-covalent, intercalation, and covalent. In case of non-covalent and intercalation, as we can, the driving forces are chemisorption, pi-pi interaction, ionic interaction, and hydrogen bonding. On the figure on the top right, you can see some of the molecules that have been used to intercalate graphene sheets, such as quantum dots, fullerenes, carbon nanotubes, DNA, and protein. In case of covalent bonding, there are two ways, like modifying the oxygen functionalities on the surface, which are hydroxyl, epoxy, and carboxylic acid, or establish carbon-carbon bondings by using diazonium salts. At the bottom, I'm showing the click reaction, which is my favorite reaction, and I've used it a lot in my research. It is the copper catalyzed azide and terminal alkyne cycloaddition. The catalyst here is copper 1. Copper 2 is used first, but which is reduced by sodium ascorbate to copper 1. As we know, sodium ascorbate is the green reducing agent for graphene, so it was like two birds and one stone. I will move on to my own research. I started work, I'm an organic chemist. I worked on organocellular molecules during my master's, but I moved onto material science and mostly graphene oxide during my PhD. I wanted to develop some adsorbents for wastewater treatment. And I thought I should go with something that is easily adsorbed and separated from the solution media. So I came up with the magnetic nanoparticles. Why did we move so fast? Sorry. So I came up with the magnetic nanoparticles. Here. Graphene is known to be why everything is like moving. I have no idea. Graphene is known to be a good substrate to grow magnetic nanoparticles. And to further stabilize the nanoparticles, I attached glucose molecules onto the graphene sheets using click reaction. I had like two approaches. In one of them, an azide molecule was introduced onto the sheet, and in the other one, an alkyne molecule was introduced onto the glucose, and they were clicked together. And during click reaction, reduction was also did also happen. Then with co-precipitation method, magnetic nanoparticles were just deposited onto the sheets. As you can see on the right side, after adsorption, we're just placing a magnet near the vial, close to the vial. The adsorbent readily gets separated from the solution media. And it only took 30 minutes for both composites to reach the equilibrium. And the other two, in the other approach, I did the opposite. So alkyne molecule was introduced onto the sheets, and azide went onto the glucose molecules. Then they were clicked together. Magnetic nanocomposites were prepared. Let me tell you about the stability of the dispersion of the hybrids without the magnetic nanoparticles. Because of having like so many OH groups, the first three were stable in water for 2 weeks, and this bottom hybrid was stable for 3 weeks since it had more OH groups. Methylene blue as a cationic dye was selected. Adsorption reactions were carried out, and again, it took like 30 minutes for these hybrids to separate to reach the equilibrium. And what I talked previously, magnetic nanoparticles were attached like physically. It was a non-covalent attachment onto the sheets. I decided to see how I can attach nanoparticles chemically onto the graphene sheets. So I modified the nanoparticles with azide, put the alkyne on the sheets, and then click them together. And here's what we got. Even in SEM images, I could easily see that the nanoparticles were at the edges of the sheets. Since this composite does not have a specific charge, I use a cationic and anionic dye for adsorption. In the other part of the research, I attached like carboxylic acids onto the graphene sheets to prepare magnetic nanocomposite, because acid groups can also stabilize the magnetic nanoparticles. Methylene blue was used as for the adsorption, and well, and as you can see at the bottom picture, at the bottom photo, a normal magnet can easily separate the composite from the water dispersion. In China, my boss was a rheologist who was totally interested in having some food for his rheometer. So we started working on graphene-based polymer nanocomposite. There are two ways to attach a polymer onto the graphene sheets. On the left side, you can see the in situ hybridization, which is also called grafting from, in which an initiator is placed chemically attached onto the sheets, and the polymer chain grows from the sheet. The issue here could be less control over the molecular weight and polydispersity. The other approach is ex situ hybridization, which is called grafting onto, and it is shown on the right. Here, well-prepared, like well-designed and well-tailored polymer chains are prepared previously and then attached with a chemical bond onto the sheets. The challenge here could be the hindrance, and maybe not many chains could just attach onto the sheets. I went on with the in situ hybridization and used my favorite click reaction for this purpose. We started with N-ethyl acrylamide and N-isopropyl acrylamide monomers. The structure of these shown on the left side. As you can see, N-ethyl acrylamide has one less methyl group, which makes it a bit more hydrophilic than the lower monomer. The graphene sheets were modified by azide, and I designed an alkyne raft. This raft agent was suitable for the polymerization of these two monomers. And then they were clicked together. During the click reaction, graphene sheets were also reduced. Then we prepared homo and copolymers using these two monomers. So here are some results. At the top left, you can see that the molecular weight of the polymer reduced by increasing N-ethyl acrylamide ratio, because it is more hydrophilic and the sheets are hydrophobic. So this repulsion is the reason for this. We also saw a linear relation between LCSD and N-ethyl acrylamide loading. And with these composites, we just could tune the LCSD from 30 degrees to 80. But we noticed something quite strange in the XRD pattern shown on the right. There was this small sharp peak only in case of N-ethyl acrylamide homopolymer, but nothing crystalline was supposed to be here. In SCM images, we saw these tubular structures only in case of any triacrylamide, as shown here on the left. AFM images show that these tubes are hollow with the Young's modulus of 80 megapascal. We speculated the mechanism of formation like this. Since any triacrylamide is more hydrophilic than N-isopropyl acrylamide, and the sheets are hydrophobic, the polymerization tends to make this repulsion and ends up to rolling of the graphene sheets. Further, I decided to see if we could have control over the polymerization if we started polymerization from in between the sheets. So I designed this raft agent with a double functionality, attached cross-linked graphene sheets with this, and went with an amino acid-based monomer, which is hydrophobic. We did a polymerization with 3 different monomers to initiate a ratio. As you can see on the right, the polydispersity index was close to 1, and we had good control over the polymerization. So we could really go with this method, we could obtain well-controlled raft polymerization. To prepare a hybrid which was compatible with the hydrophobic polymer like PDMS, I designed this reaction in which silicious-coioxane was used to cross-link graphene sheets. Silicious-coioxane is an 8-arm molecule. It was decorated with azide moieties. Alkyne part went onto the graphene sheets, and then they were like clicked together. And in this way, I reduced the restacking of the sheets because these moieties went in between the sheets. For comparison, graphene and reduced graphene oxide was also used to integrate into PDMS as a filler. Different filler amount was prepared, rheological measurements were done, and we observed that in case of our hybrid, we reached a lower percolation threshold, and it was a way better filler than GO and even reduced graphene oxide because we reduced the restacking using these silicious-coioxane moieties. I also worked on CVD prepared graphene. We published 2 papers here. In one, slightly oxidized graphene was prepared using CVD, and it was compared to chemically prepared graphene oxide. And in the other one, graphene oxide dispersion was dropped onto the graphene foam. That's why we call that mixed dimensional heterostructure. And it was used in hydrogen evolution reaction. Back in Czech, we were interested in single atom catalysts. I will refer them to as SACs from now on. SACs are isolated metal atoms or clusters which are stabilized on a suitable support. Downsizing makes the metal to be cationic and also enhances its catalytic activity. As you can see on the top left, there's growing interest regarding SACs, especially in energy storage application, like batteries and supercaps. On the right, you can see in that different atoms like iron, iridium, cobalt, and rhodium were introduced as SACs onto the carbon supports. There are different ways to prepare SACs. The feasible one is like wet chemical road, which we use. But there are challenges here. you need to have low loading amount, because if you increase the amount, aggregations will start and nanoparticles will be obtained, which we don't want that. We need to optimize the interaction between the single atom and the support by introducing defects, vacancies, and doping. And also high-end characterization methods are required. Here on the right, we utilized graphene acid and graphene cyanide, which were developed in our center from graphene fluoride. They were our supports. Copper was used as a catalyst for an organic reaction. How we did the reaction was like this. Cyanographene or graphene acid was sonicated in DMF, is stirred for some time, like for a day. Copper was added in a specific amount, and simple stirring was carried out for a day. A quick washing was required afterwards, and quick freeze drying was also essential to like avoid the aggregation and agglomeration. As you can see, the HRT images at the bottom, well-dispersed sacs were prepared. And also you can check the coordination with XPS as well. Back in Korea, I was working on two projects. One was the mass production of 2D graphene mesotubes. Previously, our group developed these mesotubes using a rheometer, rotational rheometer. So they apply shear onto the graphene sheets, and they saw that they obtained these tubes. They wanted to see if we could go with a large scale production. Two glass plates were taken. One of them was like fixed on the bench. The other one was covered with aluminum foil, scrubbed with metal scrubber. A specific amount of graphene dispersion was put on the fixed plate. The pH was like 2.2. We observed that if the pH goes above 3, we cannot obtain these mesotubes. So we kept it at 2.2. The upper glass was slid slowly at a specific rate, which applied the shear, and mesotubes were formed after 40 minutes. The mechanism that we explained like this. At the pH 2.2, carboxyl acid groups of graphene oxide are protonated. At those pHs, aluminum can reduce hydrogen ions, which leads to an increase in the pH. So the carboxyl groups deprotonated, and aluminum ions can act as a crosslinker between the sheets. So when the sheets like put like this together and the shear is applied, they can start like rolling. The final pH was 5. In the lower image, you can see the cross-polarized images of the mesotubes. The first one is at the rest state. B is like when bending, and C like after bending. So they're like quite flexible. As a proof of concept, we use this single mesotube as a sensor. How we prepared the device was quite simple. We took an insulator, taken a single mesotube in a wet state, put it on a polyimide tape, dropped oil on it to prevent shrinkage and drying. Two sides of mesotube was attached an gold wire fixed with a silver paste. It was attached to a Keithley device to get the IV curve. As you can see at the right bottom picture, like figure C, the resistance decreased by increasing the temperature. We also checked that its sensitivity to vibration. a mobile phone was placed in a specific distance from the sensor. When this vibration started, the voltage increased, and after cutting the vibration, it was decreased. So it was it could act as a sensor to vibration. Also, we checked it for the human arterial pressure. This simple sensor was put on a wrist of a male, and it could detect the pulses, and the voltage changed by each pulse. The project that was in charge was an industrial one based on silica self-cleaning hydrophobic surfaces. As we know, silica nanoparticles were around since mid-1800s. There are different ways to prepare them. Sol gel method is the easiest way. Organosilants are added to a specific solvent, which are commonly water and ethanol. Hydrolysis and condensation happen, and depending on the way you dry it up, you can obtain aerogel, zero gel, or cryogel, or even nanoparticles. The parameters affecting hydrolysis and condensation are the pH, type of precursor you use, the ratio of the water to the precursors, temperature, and the type of solvent. Coating methods could be deep coating, spin coating, spray coating, and blade coating, which we use spray coating. At the bottom images, you can see these surfaces. These material can be applied to solar panels, the windshields, and even protect the frescoes. And here's what I did back in the lab. I chose tetraethyl orthosilicate and hexadecyl 3-methoxysilane. The structures are shown on the top left. The long chain of HDTMS was in charge of hydrophobization. They were added simultaneously to water and ethanol. After 15 minutes, the ammonia was added as the catalyst. It was stirred at 60 degrees for 2 hours, and we got our soap. No aging was needed. A specific amount of sol was taken. It was sonicated using tip or bath sonication in water, and then immediately spray coated on PET films. We observed that at a specific concentration of the sol, we obtained a super hydrophobic surface in which the droplets rolled and did not pin onto the surface, showing we couldn't obtain really the water contact angle in this case. Also, the cleaning properties was tested with putting some graphite on the coated surface with only a few drops of water. As you can see in the bottom image, it was easily cleaned. This research is quite different from what I explained lately. A year ago, I was invited by an old friend to participate in this project they were carrying out on wearable devices. The collaboration was between University of Saskatchewan and Taipei University. The PIs were like health informatics specialist and also a computer scientist. The goal of this research was to see how accurate these wearable devices like watches that we wear, the PPG sensor implemented in them in telemonitoring health status. Like we started with the PPG sensor and went with heart rate, heart variability, blood sugar, blood pressure. We checked the limitations and the gaps in the science. We submitted this review and it's under revision in telemedicine and e-health. And the other review that we are currently working on and which is almost ready to submit is to see how PPG can detect stress mostly. because especially during the pandemic, a lot of people were struggling with mental health issues. And the target journal for this is like MPJ Digital Medicine. So this brings me to the end of my talk. I would like to express some fields of interest, but first let me tell you that I would like to establish a group in which equity, diversity, and inclusion are applied. This is quite important for me. In case of the fields of interest, here are some, but not limited to these. Surface modification of graphene oxide or other nanoparticles for sensors and energy storage application. Also for biomedical applications such as drug delivery. I would also like to go beyond graphene, especially to MXenes. As we know, MXenes are this new class of material of the 2D families, where they are prepared from max phases. M is a transition metal, X is carbon or nitrogen, and by delamination of these, the A metal, which is gallium or aluminum, we can achieve these 2D layers, which have, again, like graphene, they have excellent mechanical and thermal and optical properties. Back in 2019, when Professor Gogotse was giving a talk in our institute, who developed MXenes for the first time, I asked them whether they have done any functionalization on the surface because it has oxygen functionalities. And he was like, not yet. But since then, lots of functionalization have been done. But since there are 150 max phases experimentally synthesized, but only a few of them were studied. So I'm quite interested in functionalization of these MXenes towards applications like additive manufacturing and electromagnetic shielding. Well, thank you very much, everyone, for attending this talk. So I'm really happy to be here, and I would like to hear your comments, please. Yes, please.
I'm talking.
Yes, please. Yeah, I can hear you.
Yeah, thank you for the presentation. It was really interesting for me. I want to ask you if it is, since you are making some functionalization, you may use two different functionalization monomers with two different functional groups. Have you tried these kind of functionalization? Because it can be used for different polymerization applications.
Yes, sure. I have seen them in the literature. Personally, I have not used them, but we can choose different molecules. Some of them interacts with carboxylic, the other one interacts with epoxy. So I don't think that's a problem.
On the same molecule, you have two different functionalization, and you are using one functional group to attach to the graphene for the graphene oxide functionalization, and the other one, which is free on the graphene oxide, also a functional group.
Yeah, that's possible. That's possible, but I have not done it.
Have you seen UV curable applications? Because the color is black, and I'm not sure if you can apply UV curable polymerization or not. Have you noticed any application on this?
UV curable? No,
yeah,
we just did like polyaniline. I've also did some polyaniline polymerization and also raft agent. That's what we have done so far.
Okay, thank you.
Sure.
Any other question?
One more question.
Yes, please.
Have you tried sol gel polymerization at the same time when you are making sol preparation for graphene oxide? You solved some sol gel method to make it. if you add two sol gels together to make polymer and also the graphene oxide, you may get very different composite material. Have you tried or have you seen any?
No, in case of sol gel, we just worked with the silicon nanoparticles only. We didn't go with polymers.
Yeah, you can go.
Sure.
Yeah. Thank you.
Mina, I have a few questions.
Please.
Can you hear?
Yes.
Yeah. First of all, welcome to Sunum.
Thank
Good
you.
to see you in Sunum, the cohort. First question is, you said, the under acidic conditions, you can roll up graphene oxide and produce, the mesotubes of graphene. So if you consider, the synthesis conditions of graphene oxide under acidic medium, why we don't observe, such a rolling, the procedure in solution? Technically, you are using solution phase and you are just using aluminum there. And can you use something different in solution phase to roll them up rather than just using two different plates? Is it possible to produce in situ?
We didn't observe, no, it was not. We tried that. Like in situ, you have a beaker with a solution of graphene oxide, with the dispersion, nothing was observed. We need the shear.
No, I mean, did you add any aluminum, cation?
Cation, yes, we did. But we need the shear. That shear is crucial for this rolling up. In case, this is what we observed.
So can't you apply, the shear force mechanically? I mean, rather than rolling somehow, you can apply probably, the shear force in the solution phase?
We did not do that.
All right, so.
Yes, we just did it in the rotational rheometer. That's what we get. And also then with the plates. All
right, thanks a lot. Second one is single atom catalyst.
Mm-hmm.
So generally, everyone is, defining this term as a single atom, but, in theory, most of them are, the clusters.
Clusters, exactly.
Yeah, so what was the size distribution of your, the single atom, the clusters? I mean, the single atom clusters.
Yes, that's
from
what,
the,
I don't recall exactly.
So we can see, the spots there. Yeah, they are there, clearly homogeneously distributed on the, the surface. Yes. So what about the, the size distribution? Do you have any data related to size distribution?
I think there must be in the paper. I don't recall right now, but I can check.
All right, so.
For you. But you see, as the mapping shows, at the mapping shows like quite well distribution, and the sizes are very, very small.
Yeah. I'm just trying to, to figure out what is the size. So because, if you aim some certain journals, I'm trying to figure out, whether it will be accepted as single atom, the catalyst or not. So is there any, the threshold to say, all right, if it is below, the 0.5, people will consider it single atom. Or if it is, the 0.1, then how are you going to, observe it by the, the current techniques? If we study, the here single atom catalyst, what is the best technique to spot, that single atom catalyst? If you don't have, enhanced, the characterization techniques there, Xanax, X-Fax, or different things. So how are you going to, figure out they are single atom catalyst? So better to test maybe catalytically and then evaluate, the test and come from there to the backside, do further analysis.
Exactly, that's how we approach. When we, after preparation, we didn't really want to go first for dark field microscopy. So what we did was TEM in the beginning. So we took it to TEM and we saw no particles, just the sheets. There were no nanoparticles. So we said, yeah, we don't have nanoparticles. So maybe the single atoms were prepared. So I'm also XRD, and then we went with these high-end characterization methods. But without them, it's really difficult for characterization. We really need at least like a couple of them.
Thanks a lot.
Sure.
There is a message in chat box. Sarah Samoe, thanks to you, Mina hocam.
Yes, she's an old friend.
Thank you, Dr. Mina Namvari, for your presentation, and thank you all participants for your participation. Next week, we will have Professor Ahu Altınkut Uncuoğlu. Her subject will be knowledge and technology transfer on the axis of agriculture. See you all next week.